Hey Calc, happy Friday. We are on to the second half of section 3.3 notes. Homework assignment is here again. In the first half, we kind of talked about how you always want to try to plug a limit in if you can plug the limit in. You always want to try and test that first. And then we kind of started getting into, what you do if you cannot plug the limit in, like if there's a hole or something, like we saw with this function here. And one of the things that we decided was, okay, if it's written in a fraction like that, let's try to do some long division and then use that result from our long division to plug the limit in. And then we may get an actual answer. And we did in this case. We actually got the value of 3 when we plugged the value of 1 in for our limit and our result that we got from long division. Okay, so on to the second page, they kind of talk about a strategy for finding the limit. And in this first bullet point, they say, learn to recognize which limits can be evaluated by direct substitution. Okay, you should be able to direct substitute anything that does not have a domain error. Okay, so remember that those domain errors involve errors are negatives inside square roots and dividing by 0. Okay, so like some of these ones up above here, like this one we had to worry about dividing by 0 because I had a fraction. But like this one, this last one that we had right here, this was a cubic root, right? So I don't have to worry about a negative inside of a square root because you can have negatives of cubic roots, right? This one here did have a square root, but notice that inside here, x squared is the value that we're plugging in, which means that that guy is never going to be negative, right? So I'll never have a negative inside of that square root because I'm doing x squared plus a number. So that number inside of there will never be negative, so we didn't have to worry about that. Okay, this one, we do have to worry about something. We have to worry about dividing by 0 because if x was -1, we would have a 0. But the limit that we're plugging in is not even -1. It's a positive one, so we don't have any problems here. And then this really doesn't have any domain errors. We don't have a square root. We don't have a division. So I can just plug into that, okay? So really just look at those domain errors. If it doesn't have one, you should be able to just plug right in and solve and be done, okay? Then they say if that fails, if you cannot directly substitute, you try to change f of x to some function, to some other function which we call g of x, okay? So like f of x up here, I'm making a really big mess of this diagram here. F of x was this function. What we did was we used long division to change him to this function, which we call g of x, and then we evaluate the limit of g of x, okay? So we're just changing and kind of dividing out that whole, I guess, is what you would say. So number 2, if the limit f of x as x approaches c cannot be evaluated, try to find a function g that agrees with f for all other values, like dividing that out. And then substituting that in. So bullet point number 3 says instead of plugging the limit into f of x, we're going to plug that limit actually into g of x because you will not end up with any problems. And then whatever pops out is your actual limit. Number 4, you can always use a graph or a table to reinforce your conclusions. So you can look at, the curve, and as it's coming in from the right, as it's coming in from the left, you are looking for the y coordinate. Okay, so when they say the limit as x goes to, let's say 1, they're saying if the x coordinate is 1 on that graph, what will that y coordinate be? You're looking for that y coordinate, okay? And there may be a hole that exists there, but on either side, it should give you, by looking at either side of where that hole exists, it should give you enough to see where that hole would have a y coordinate if it actually did, okay? So dividing out is one of the techniques like we used in the last example on the first page. We're going to do that dividing out example again here. They are wanting us to find the limit as x goes to -3. And remember I said that sometimes it'll be written with that off to the side. Most of the time you'll see it where that x goes to -3 is on the bottom. But the limit as x goes to -3, if we try to physically plug -3 in here, we'll end up with -3 squared plus -3 minus 6 over -3 plus 3. And whatever this top comes out to be, I think it comes out to be 0 actually. The bottom comes out to be 0. So this is the part that I really have a problem with. Problem, bad. We cannot actually plug the -3 in. So we have to do another technique. And because this is a fraction here, this addresses domain error. I don't remember which one I called it. Domain error number 2, which was dividing by 0, and I don't want to divide by 0, okay? So to fix that, I do my long division, okay? So I'm going to do some long division over here off to the side, and this is just going to be short, quick long division. X squared plus x minus 6. X plus 3 is on the outside. I don't have to insert any zeros in there because he has everything that he needs. And then what I'm going to do is take, what do you take times x to get x squared? And that is x. X times x is x squared. X times 3 is a positive 3. And then you flip the sign. Minus, minus. Cross off. I'm going through this kind of fast, so if you need to pause, go ahead. Positive x, oh, I forgot my x. No. Yeah, I forgot my x on my 3. Positive x minus 3x is negative 2x minus 6. I drop the 6 down. And then I begin again. So what do you take times x to get negative 2x? I need a minus 2. Negative 2 times x is negative 2x. And negative 2 times 3 is a negative 6. I flip the signs, and my remainder is 0. So x minus 2 is what I get when I divide that out. So rather than taking the limit as x goes to negative 3 of this function, I'm going to take the limit as x goes to negative 3 of x minus 2. And then what I can do is just take negative 3 and plug it into there. So I do negative 3 minus 2 equals negative 5, and that's my limit, okay? Now, I can hear Wynn screaming at me right now, like, why are you doing long division? Check this guy out. This is probably, I don't know, and maybe Wynn, you didn't come up with this, so I just give you credit for something you didn't do. But this top part right here, x squared plus x minus 6, he is a simple trinomial. And a simple trinomial breaks down into 2 pieces. What can you multiply together to give you negative 6, but when you add them, give you 1. And then it's x plus 3 and x minus 2, and you have x plus 3 on the bottom, and all you need to do is cross that out, so you get x minus 2. So sometimes if you're given a trinomial or even a difference of squares in the numerator, you don't have to do long division. You could just factor it and then divide that out, okay? So like another example of that might be like, let's say I have x squared minus 4 over x plus 2, and I'm trying to find the limit as x goes to negative 2, okay? I can't plug negative 2 in here because I'll end up with 0, but I could use long division if I wanted to. But rather than doing long division, we see that x squared minus 4 is a difference of squares, and he breaks down to x plus 2 and x minus 2 is what that difference of squares is, right? Like the square root of x squared is x, the square root of 4 is 2, 1's plus, 1 minus, and so then those two can just cross off. So all I need to do is find the limit as x goes to negative 2 of x minus 2, and if I plug negative 2 in there, the limit is negative 4. Okay, so sometimes factoring is a little bit faster than actually dividing it out, you know, and you can do that as well. So the dividing out technique, I'm going to say, or let's do this, or factor. If you can factor, you know, that makes it a little faster, right? The rationalizing technique. Okay, so when you have problems, I'm kind of all over the place. If you need to finish writing. If I'm going too fast and going on to the next problem, go ahead and pause it and finish writing, and then unpause. Okay, the rationalizing technique. This guy addresses domain error. I think I called this error 1 up above here. Domain error number 1, which was dividing by, or a negative inside of a square root, because I have a square root. No, it doesn't either. It doesn't either. This one kind of addresses domain error number 2 again, where I'm dividing by 0. Because if I have 0 and I plug it into that bottom there, I'm going to end up with 0 in the denominator, and I cannot have that, okay? Now, rather than dividing this out using long division, because I don't really know how to divide that thing out using long division, what I'm going to do instead is called the rationalizing technique, okay? And we did this, did we do this just recently? Yes, we did in the last chapter when we did i's, okay? When we would have like 3 plus 2i, you don't necessarily have to write this down. and let's say 4 minus 3i. Okay, we did not like the I in the bottom, so what I would do to rationalize that is I would multiply by the conjugate. So I would multiply by 4 plus 3i and 4 plus 3i on both the top and the bottom. And by doing that, when I FOILed this part, the I would end up going away, and I would not have an I left over in the bottom. Okay, we're going to kind of apply the same type of thing up here, except instead of doing the conjugate of the denominator, I'm going to do the conjugate of that numerator. Okay, so I have the square root of x plus 1 minus 1, and I'm going to multiply him. The conjugate of him is the square root of x plus 1 plus 1. That's what I'm going to do for his conjugate, the square root of x plus 1 plus 1. I have to do the same thing to the top as I do to the bottom in order to make it legal. Okay. And so as I go through this, I'm not going to simplify some things. So go at the same pace that I am, because there's some things that I'm going to not simplify on purpose. Okay, so let's do this top part first. Really, this top part is a binomial. We have two pieces. We've got this piece and this piece, and this piece and this piece. So we are actually going to FOIL this. So the first thing that we're doing is the square root of x plus 1 times the square root of x plus 1. And if I have two square roots, they end up just popping out as x plus 1. Square root of x plus 1 times the square root of x plus 1 is just x plus 1. If I multiply this guy over, I have plus 1 times the square root of x plus 1. Okay, if I multiply my middle two pieces, my inside pieces, that would be negative 1 times the square root of x plus 1. And then my my last pieces are negative 1 and positive 1, which is another negative 1. And what you will notice here is that these guys are going to cancel out, but also this positive 1 and this negative 1 cancels out. So all I have left on the top is just x, okay? Now, on the bottom, I have x times this and x times this, right? Because this is a binomial. But rather than distributing that x through, I'm going to leave it as x times the square root of x plus 1. I'm not going to simplify that because these two x's can cross out with each other, right? That x is left on top, and he's the only thing on top. So I can cancel those x's out. Now, we've canceled the x on the top. We've canceled basically everything on the top. So what's left on the top? We write 1 when everything else cancels. And on the bottom, we have x plus 1 on the outside. And this right here is kind of like our g of x equation that we're going to switch it to. This was f of x. This was our original equation that we were not allowed to plug 0 into. But let's see if, now that we've rewritten the function in an equivalent form, which we call g of x, let's see if now we're able to plug 0 in, okay? So if I plug 0 in, I get 1 over the square root of 0 plus 1 plus 1, okay? 0 plus 1, this would be just the square root of 1. And the square root of 1 is 1. So I have 1 on the top and 1 plus 1 on the bottom, or 2, and 1/2 is going to be my limit. So I don't end up with any problems in that case. That was the rationalizing technique. I'll zoom out quick. And rationalizing, we're going to multiply by the conjugate of that numerator part, okay? All right. The last thing that we're going to talk about is something called the squeeze theorem. And yeah, the squeeze theorem, here's what it says. If I have three functions that are in this relationship to each other, like h of x, f of x, g of x, where h of x is smaller than f of x, and f of x is smaller than g of x, what I can do is I can find the limit of these two guys and use that to squeeze this guy in here and find the limit of that one, okay? So I gave you an example down below here where I have h of x, f of x, g of x. And what we can see is that x squared, oh shoot, I should have rewritten these in another order. Oh, switch these around. Let's do, this guy is going to be my negative and this guy's going to be my positive. So just change those signs. So we have negative x squared plus 2 is less than just x plus 2, which is less than, I'm going to say or equal to, I guess, positive x squared plus 2. Okay, the thing that's staying the same is the 2 part, right? 2, 2, 2. But I would say that negative x squared is going to be smaller than just x, and just x is smaller than x squared. Okay, now exclude the fact that we are like never mind. I'm not even going to get into that. I'm not even going to get into that. Okay. So negative x squared is smaller than x, which is smaller than x squared. That's the way I'm going to write that in that order. Okay. So let's talk about the graph of what these guys look like for just a second. Negative x squared plus 2 is a parabola that's facing down, but it is up at 2. So he does one of these. Okay. Now I'm going to talk about, so that was this first one. This second one right here, positive x squared plus 2 is just a parabola going the other direction. Okay. And if I'm trying to evaluate, let's say if I'm trying to evaluate the limit as x goes to 0 of x plus 2, okay, I'm looking at this guy. What I can do is x plus 2 is the linear function right here that goes, well, he's really going up 1 over 1, up 1 over 1, down 1 to the left 1. He's a linear function that looks something like that, right? He's kind of squeezed in between those two functions. And so what I can see is if I'm looking at the limit as x goes to 2, or x goes to 0 of x plus 2 is in between these two functions. So what I can do is I can look at the graph of these two functions, or even plug my value into those two functions, and I see that as x is 0, each one of those has a y coordinate of 2. Okay, and because my function, the one that I'm interested in, the middle one, because my function is squeezed in between those two guys, he is going to have the same limit as what these two guys have. And these two guys, their limit is the same as their y coordinate, which is just 2. So the limit of this guy is 2. The limit of this guy is 2. So since this guy lives in between those two, his limit must be 2 also. Okay. So you can kind of see that from the graph. Typically, we don't graph them because we just plug the limit into this one, plug the limit into this one, and then that allows me to find the limit of this guy, you know, and just do it that way. But looking at the graph, you can really see why that is true, because that line is squeezed in between those two parabolas. Okay? All right, squeeze theorem. I don't even think I asked you a question on your homework assignment over the squeeze theorem, just because, you know, that's kind of a higher level thinking-ish thing that you guys will deal with in college, probably, if you take calculus. And I don't focus too much of our time and energy on the squeeze theorem, but there's an introduction into it just for you. Okay, get to working on that homework assignment. I know it's Friday, so these are shortened periods. I don't want to make this video last any longer, so goodbye.